and otherwise, I will send it to people right now as an email. So here we go, and okay, but I would suggest that you consider muting your device. Otherwise, we'll have a cacophony of a familiar voice, which would be of mixed pleasure to those in the room.
Hey, do you like your voice when you hear it?
No, no, I don't like my voice. No, I greatly dislike my voice, but that, yeah. Okay. Okay, and if anyone is having trouble, I'm sending it out right now via Moodle to everyone, and you could attend with that. So, our class session is available at, here we go. And I'll send the message. Boom. Okay, so you also should have a message which will link you directly to the event. Are people able to access it by and large? Okay, great. So we're going to get going. I asked you for today to read a chapter of the book, to it, chapter 3, and that chapter introduced a set of material which unites some conceptual material on various topics with practical understanding of Java as a language. And reflecting that, my aim for today is to weave the two together, okay? And go a little bit deeper on some of the topics discussed, or hit on additional perspectives on the topics discussed that are conceptual in nature, things like immutability and data sharing, pattern matching, currying, recursion, etc. At the same time, to give you, thanks very much, Wade, a concrete sense of the language support for a lot of these mechanisms, which the book doesn't go into in as much detail as it could for various didactic reasons. Now, we're going to have some hands-on exercises. This will be a key component here. And you are encouraged to call up Scala in one form or another so that we can follow along together these exercises, which will involve a set of these topics. As I say, the chapter covered a number of disparate things, and we're going to have time to explore only a subset of these. For example, I talked about equational reasoning last time. The chapter used that at several points. It used this kind of tracing. Do you remember that? Where it expanded an expression into its definition and successfully did that so that it was progressively expanded and then simplified. So they use that to sort of help the reader understand sort of what's going on here in successive lines. That's an aspect of equational reasoning. You know, if we have A defined as this, we can, wherever A appears, we can just substitute in the thing to which it's defined. I'm not going to go into that more today, but it's going to be a key thing we kind of assume along the way. More than that, we're going to be talking about a number of elements associated with things like companion objects, tuples, potentially, a special Scala syntax for list that I'm not going to go into in great detail, but I want you to know about them. And we're going to use them through the class and in the later part of the class as well. There's some things the book touches on, like type variable, type parameter covariance, that if you have A as a subtype of B, a list of A is a subtype of a list of B. They have this plus notation for type parameters. We may come back to that later in the course, but we're not going to go into it now. And this whole notion of algebraic data types is a theme which will run through the book. We might talk about it a little bit later in the course, but it's not going to be a big element of the course because it doesn't bear as much on the goals of the course. We will talk some about multiple parameter lists and their link with this notion of currying. Okay, so ladies and gentlemen, what I'm going to ask you to do here is to fire up your Scalas. And if, my suggestion is to use Zeppelin for that purpose, but, you could alternatively use the Scala command line if you'd prefer, okay? So I'm going to start up my Zeppelin as well, and we'll get going here. Okay, so over here, and let's see. Okay, and here we go. Oops. Okay. Start Zeppelin. Okay, so as you know, Zeppelin is started by firing up a command that gets a port open on your computer, and once that's open, you should be able to go and access it. It's going to take a few minutes here. And we're going to use the Zeppelin command line to explore in Scala a number of these topics in the course of our lecture. And the first one we're going to start with is actually lists. Much of the chapter was devoted to lists, but not lists for their own sake, but lists to illustrate a number of principles involving functional programming. These principles include aspects of recursion, aspects of type parameterization, aspects of pattern matching, etc. And we're going to actually use a somewhat different syntax for this need for lists. That's a syntax supported by Scala natively. For the book, the interest was in making sure that that everything was clear and defined. And why is this? There we go. That's just hidden. Okay, so what I'm going to do is I'm going to create a list in Scala, okay? And this is going to be called my list. And I'm going to do so with a list of strings. So lists in Scala are type parameterized. What do I mean by type parameterized? What does it mean for something to be type parameterized? List is a data structure and it's type parameterized. What does that mean we can do with it?
Make a list of any type.
That's right. That's right. So we can make a list of ints. We could make a list of doubles. We could make a list of persons. We could make a list of lists. And the type parameterization is something that allows us to essentially tell it this is a list of X, and X will vary. It's a parameter, but it's a type parameter. It's not a parameter we pass to a function so much as a parameter that that specifies the type on which something operates. In this case, the whole list data structure. So we're just getting Spark running here. And what I've done here is I've created a list. Do you see it on the screen here? I've created a list which consists of two elements and then a final element, which is just the termination of the list. So it has foo and bar in it, and then it's a termination of the list. And you'll notice that I use this special syntax here. How did they in the book denote this syntax, : : Does anyone remember? They use this special term. It's actually drawn from Lisp called cons. They cons this with that, and that has a long history in the Lisp and functional programming community because of Lisp. And you'll occasionally hear me saying I'm going to cons these things together, but fundamentally in Scala there's this extra brief kind of syntax where you use double colon. Okay. And I might not note that Scala tries for brevity in its notation for many things. For example, we could create here, and this is just an aside, a stream like this, okay? And a stream is going to make use, it turns out, of a very similar notation, but it will be just a variant of this. I want you to know about this because you'll sometimes use it. I'm going to create a stream with the similar elements. And what I'm going to do is I'm going to write this. This little hash sign, colon, and then I'm going to write bar, and I'm going to write, and actually I'll just include those two. Oops, it's not a member of string, right? Okay, so I'll do bar and nil. Okay. Oh, okay. Maybe we have to do this. I'm going to have to check. This is an aside. It's an aside down a dead end. Okay, there we go. So this is a way we can construct a stream out of several elements. So here we're using this kind of append operator for streams to cons up a stream, to create a stream, just as we do for lists. But our focus today for the first few minutes is going to be on lists. And with a list, we can do my list, we can ask for its head, or we could ask for its tail, right? Here we go. And this will allow us to kind of walk down the list, taking successive elements of it. We're going to go and make use of lists for the next couple minutes here for a couple simple things. I should note that this notation of the colon is purely convenience, because you can always type the following. You can always type list of foo, comma, bar, and this will also work just fine for building up a list of multiple items. Okay. Now, one of the goals of the chapter, and one of my goals today, is to make sure you're aware of the potential for using these in a way that's flexible, using pattern matching. Okay, and what I'm going to do here is go and define a method which is going to operate on lists. Okay, and it's going to operate on lists at first of a specific sort, list of doubles, and then it will operate on lists more generally in a type parameterized way. Okay, now the way in which I'm going to do this is I'm going to use a syntax introduced in the book for defining methods. Does anyone remember what's the syntax to define a method, to declare a method within Scala? Define it. Yeah, although we'll make a distinction between functions and methods. And actually, at a technical level, I'm going to define a method. But I'll show you how you can convert it to a function in a few minutes. But there's a special syntax in Scala to define a method. Does anyone remember what it is? What's the keyword? Def, yeah. And so, we could define a method which is going to operate on lists here. So I'm going to create a method which is going to be called myJoin. Okay, and myJoin is going to join together elements of a pre-existing list passed to me. So there's going to be a list passed to me, which is a list of doubles, okay? We'll come back and genericize it. And there's going to be a separator, which is going to be a string. And basically, the goal of this is to return a string. So how do I indicate this returns a string? Anyone? How would I indicate that this method returns a string? What do I do? Well, I say, yeah, I use colon and say string. Now, that's right. So here I am going to then declare the body of the method. In order to declare bodies of methods in Scala, you need to put if it returns a value. This is very important. You put an equal sign. Okay. If it doesn't return a value, if it just does something, if it's what we might be called procedure, it's a routine. It just does something. It doesn't return a value. We don't need the equal sign. Okay. We'll sometimes say it returns unit, but we don't need the equal sign. Okay. So here we are. We're going to define my join. Can you see this on your screens here? Can you see what I'm doing? Okay. And what I'm going to do is I'm going to handle this in two cases. I'm going to say, L match here. And I'm going to match different possibilities with L. And, you could choose how you want to indent this or what have you. But what I'm going to do is do it like this. I'm going to handle it in multiple cases. Now, what's one possibility here for our handling of this? What's one thing we have to handle? Match allows us to handle different possibilities for whatever's matched, in this case, L. What are the different possibilities here that we might handle? Okay, good. So how would we write that? Well, we say case nil, and then we put a handler for that case, okay? If it's nil, we'll return an empty string. Now, if it's not nil, what are we going to do? Okay, we want the separator to be between successive elements of it. What might we do? So we want a list of like two items, A and B, to have the result be A stircep, which is this string, B. So it might be a comma, right? A, comma, B. If it's just a list, if it's only one item, we don't put a comma after it. The comma is to separate things. So how might we do that? Good. Excellent. Excellent. So we know the list isn't empty, but it may be that it only has the first item and the next one is empty. So what we can write here, and this is one of the key things I want to emphasize about this, about how this pattern matching works. You could say case H, which stands for, guess what? Head, colon, nil. If we have this, then we are going to handle it by just returning what? Well, just the string value of the head. So I'm going to say h.toString. And alternatively, if it's h colon with some tail, t, we will handle it how? Yeah, good. Concatenate the first element. Content, I like it. Yeah. Yeah. So concatenate with. Yeah, exactly. Onto the recursively defined one. Okay. So here we go. We'll knit these together like that, and this is actually h.toString because we need to convert it to a string, and then the separator, and then we will do my join. And we will join the tail with the separator like this. Okay. So it's notable this is recursively defined. In order to handle this case, we break it down into pieces. It's divide and conquer. We say, oh, we have a head. We know what to do with that. We'll just convert it to a string. We then have the separator to separate the two, and then we'll have this whole function applied to the rest of the list in the same sort of logic, right? Okay, so ladies and gentlemen, if I haven't missed anything in that definition, we should be good then. And now we can happily do, okay, you know, I'm going to create my join of 1 : 2 : and I'll put them like this so it knows the rest of it is a list. 3 : nil, and I'll pass it as a second argument to my join. I'll pass it a comma, and we should be able to get out. Ooh, okay. List. Oh, of course. What's wrong here? What sort of error is that? Yeah. Sorry, it should be a double. It should be a double because it's expecting a double here. Okay, and here we go. So it created for us a rendition of the list with commas, the separator between them. And of course, if I had called this with a different separator, if I had called it with you know, a semicolon in between, it would similarly render it that way, right? Okay. Key things, though, here. I mean, this is a little example of the sort that might be explored in a basic programming course, but there's a few key things to realize here. One is that we have these definitions which work by pattern matching of sorts. They match the items being handled, and in that matching process, they destructure it. They take it apart. They handle different possibilities for it into their pieces in a way that allows us to deal with it. And thirdly, we're dealing with it recursively, right? We're dealing with it by calling off the function. Okay, fair enough. Now, how, and that's important. We're going to talk about how this destructuring takes place. The destructuring that's occurring here is occurring through something called an unapplied operator, okay, which we'll come to. And you can use it for your classes. It's not just something that is only defined for built-in things. We can, in fact, use it very readily for our classes, and we'll see how we do that in a few minutes. Okay, but suppose I wanted to genericize this. So it wasn't just double. This can handle any sort of list. How would I do that? I want my join to be defined in a type parameterized way. How would I modify this definition? Anyone? How would I modify that? What do I need to do?
You can replace double and string with A and B.
Yeah, although here, so it's a good idea. Here, I want to always, suppose that the goal of this is to return it as a string. Okay, so we're generating a string, and the separator should be a string. Suppose I don't question that. I want this to be a list of, it doesn't have to be double. I could have a list of ints, or a list of strings, or a list of persons, and I want to be able to render any of them. What do I have to do here? Good. Yeah, so I can do a type parameterized version of this, and I'll do my join type parm just to keep them apart, okay? And as it turns out here, nothing else has to change, because it turns out not just doubles, but lots of things have two string operators. Oh, okay, so it's oh, of course. What did I do wrong? What did I forget? We have to have it call itself, not call the old one, which only operates on doubles, right? There we go. So now my join type parm can operate on many types of things. So could we give it this thing? You bet we could. My join type parm. We could certainly give it this. But we could also give it that thing which caused us trouble originally. Remember that? Where we had integers. It should be able to handle integers. And it should be able to handle strings in that, right? Foobar and Baz. Okay. And there we go. So type parameterization allows us to generalize our methods, and we get abstraction via parameterization here, where it allows us to take something which is limited to one type and to use it for many types. Now, an important point here is that in order to make use of this, it had to do some type inference. Why do I say that? Why do I say there's type inference going on when I call this? In what sense did it need to infer types? What did it need to infer? The type of what? Here.
The list.
Yeah,
Items.
the list items. And it had to infer T, which happens to always be associated with the list. We could have this work for more than T. Sorry, a list of T. In other cases, we might have T being used for many types of things. But for now, we'll drop this. Okay. Okay. Now, it bears noting that if you tried to use this with, and we'll probably come back to this at a later point. It's an important point about Scala and the way in which it differs purely from traditional functional programming. What do you think would happen if I took this, which is a list of strings, and I was to instead put in something unexpected? Like instead of putting Baz, I were to put 3.14 or 159. What do you think would happen? Okay, so you might think, okay, I won't accept it because there's no, it would seem that there's no type T, single type T that accounts for all of them. But in fact, there it is. Okay, you'll notice, see it comes back here with this. It actually handled it. It gobbled it up just fine. And you might be excused for asking, well, what in the world type T allows it to do that? And the answer is indicative of the fact that Scala is not purely an object-oriented language, excuse me, purely a functional language. It's a functional object language or object functional language. And it supports a type hierarchy, not merely independent types, which are each in their own world, that also supports type hierarchies, okay? And type hierarchies are a key part of object-oriented programming. You have subtyping and subclassing, right? But they're a key part of Scala's definition as well. And in fact, in the slides that I shared with you, and here we're dealing with a virtual world that's much larger than my screen. Let me just shrink this down. But in the slides that I provided to you, I actually indicated a type hierarchy. And you'll notice that these various types, shorts, bytes, doubles, etc., and in fact strings, are underneath certain other types. This is Scala type any here. Do you see that up at the top of this hierarchy? And double, it turns out, is a subtype relationship. It's a subtype of any. Scala object is in fact a subtype of any. String is a subtype of any. So we can in fact mix these together. We can mix and match them because they are all any's. And it figures that out. able to figure that out in terms of the types involved. So there is, in fact, a subtype hierarchy. It does sometimes come into play. And it may allow you to have a flexibility that you don't expect with respect to certain uses of these elements in Scala. Subtyping is going to be something that is very valuable in certain cases in Scala, and we can take advantage of it. Okay, so those were brief introduction there to or brief look at pattern matching at an abstract data type, namely lists, and Scala syntax for it, and the fact that we can destructure through pattern matching things into pieces. We're going to be returning to many of these issues in the course of the semester. We're going to make use of them. Okay. Any questions related to that before I go on to another topic that the book made quite heavy use of, and actually made use of it sort of as a convenience in type inference, rather than in some of the more powerful ways in which later chapters of the book might make use of it, or which we will. Any questions about what I just hit on? Okay. No questions? Okay, great. So maybe I should be asking the web viewers out there any questions. Okay. So next, I'm going to talk about an issue on type parameter, on that bears on type parameterization, and that the book used in the context of type parameterization, but which has far more significance than that chapter of the book really got into. And it's a topic that introduced a word. You may have even missed it. It may have even been hidden in a footnote in the book. And it's the word is currying. Okay. We're going to make heavy use of currying in the course of this semester. And it turns out currying, understanding currying, currying is an exemplar of the use of closures, and in fact why closures are useful. Okay. And we'll see how it's how that plays out, because it's going to be a large part of what we'll be exploring this semester in some contexts, and it will help us avoid problems and do things more conveniently. So what is currying? Can anyone tell me what's currying? If I say I curry a function, I have a function of a couple arguments, takes a couple arguments. Maybe it's an add function. It takes A and B and adds them together. What would a curried version of that function be? So if I had add, here's, I'm gonna define an add version, a sort of simple add, and I'm going to say here, I'll just do it like this at first, okay? Def my add one, okay? And it's going to take, for simplicity, an int, and it's going to take an int, and it's going to return an int, and its body is just going to be A plus B, right? This is the definition of my add, and I can happily use it to add things together and get results. Okay, now another way I could write this. So I would tell you that this is actually a method. It's not a function. And one of the ways we know it's a method, a purely syntactic way, is it's defined with def. Let me show you a function that does the same thing. Okay, val my add function. And this function is going to take in here a thing that's going to be called A. Take a method, a parameter called A. And it's going to take another one called B. And it's going to add them together. Okay? Oops. Okay, so here's a function. And you'll actually see how it responds to it is differently. This is saying it's a function. This is a method, okay? No, they're close cousins. They're very close, but it turns out there's some differences. And amongst other things, we can make methods type parameterized. We can't make a function by itself type parameterized. A method can have multiple argument lists. We'll come to. A function cannot without straightforward currying, which can be used to deliver on it. There's a couple different ways in which these are different from each other. And it's a little bit confusing to students at first because you can assume that they're the same thing, and they're actually not. But they're very similar. Now, this is a function. I want to create now a curried version of the function. A curried version of this, I'm going to call it curried add. And it's going to be a function which takes in the same parameters, but it takes them in a different way. How do I mean different way? What is it doing? One at a time. One at a time. And in general, it takes them in at a staged way. By stage, I mean it takes in some before others. Okay, so this is going to take in A, and then it's going to return. If it takes in A, what's it going to return? Yeah, it's going to return a function. And that function that it returns is going to take what? B. And then once it gets B, what will it do? It add them together. Okay. So ladies and gentlemen, this is a curried version of this one. This one took them together. This one allows us to pass them at different times. You can pass A and later pass B, because we pass A, it gives it back a function whose job in life is to take B and add A to it, whatever A was, right? Now, this may seem a weird thing and like to have no obvious value. In fact, it has huge implications in terms of how we can do things. And it allows us to do many, many useful things. It allows us to give information early that is needed and then forget about that information because the closure, the function that's returned after we give that information remembers all that information. And this brings us to the key point that these functions, when I say this returns a function, I'm only sharing with you a subset of the truth. I mean, it's true it's a function, but it's a special type of function. It's a closure. And what that means is it is a function, but it remembers certain types of information about values it needs to know about, in this case, A, that were defined. It's, as we say, it's closed over an environment that includes A. It knows the value of A under which it was created. This is extremely important. It remembers the value of A. And what that means is that later, when we invoke it on a B, it can add A to it, right? It's keeping track of all that. We could have long forgotten about A. All we know is this is a function whose job it is to add this value we specified to it long ago to things. And when it comes time to do that, it'll remember that. In other cases, we might give a curried function many types of information to remember, and we don't have to remember it ourselves anymore. It's bound up in the closure. And the closure can then act in the appropriate way, do its job in life when the remaining information is provided. And it turns out this is extremely useful. It's extremely useful to be able to do this. And an example might be on a web page. You go to search for something, and you specify something you want to search for. And a closure is created that remembers all the criteria you use. And that closure is then saved away, and we can go to the next, go to the next one, or go to the next one. It doesn't have to remember the whole criteria anymore. The closure remembers it, and the closure knows how to look for the next time its criteria is matched, even though we no longer have to keep track explicitly of that criteria because it's bound up in the closure. Okay, so let's see how we can use this thing. Okay, I'm going to look at this, and I will say I'm going to create a closure here. It's going to be a closure whose job in life is to do a very special thing. And you're going to tell me what it is. Well, it's pretty obvious. Its job in life is to add 10 to things. How would I define this? How would I define something whose job in life is to add 10 to things? What would I do using this curried add? Yeah, I'd say curried add, and I'm going to pass it 10 here. And I would argue that what it gets back, if I give it 10, what does it get back? Sorry? A function. A function whose job in life is to add 10 to things. So this has gotten back a unary function. It's a function that just takes one number and adds 10 to it, right? So let's do this, right? Here's my add 10. We're going to say my add 10 of 3, and what will I get back? 13, right? My add 10 to 2, and I'm going to get back 12, right? Okay, it's remembering all that. Now, I could create a my add 1, right? And how would I create that? Yeah, I'll call it curried add on 1. Does this guy interfere in any way with the old one? No, he in no way interferes with it. So my add 1, I could call it on, 3, and he remembers, or she remembers, that her job in life is to add 1 to things. My add 10, of course, still remembers that its job in life is to add 10 to things, right? So they coexist because they each are closed over and under a different environment. They each remember different A's, different values of A's, but they remember all these A's that are free variables here that are with respect to this inner function. They remember it because they're bound up with this A passed earlier, right? Okay, so this is an example of currying. We have divided something that normally takes a set of arguments together into a set of pieces that takes those arguments at different times. Do you see that? Okay, now, it turns out that, not surprisingly, given my statements about how important this is and how powerful it is, I don't have time to prove that to you right now, but we'll be seeing it in the course of the semester from time to time. It should come as no surprise that Scala provides the ability to accomplish this automatically with minimal syntax. This currying that I've been showing, I've tried to make it as obvious as possible what's going on by having these clear functions, and defining them as functions. But it turns out we can do it with methods, with these methods that we def. And the way in which we do it is, not surprisingly, to have multiple parameter lists, just like you saw in the book. So we can go down and we can do something like this. We can say my add succinct, okay? And this will take in one argument and in a separate parameter list take a different argument. And here we will set it equal to A plus B. Okay, now I'm being a little bit verbose here. I mean, if we really want it to be as brief as possible, it turns out we don't even have to say colon and it will figure this out. But okay, this is my add succinct. Now, this is not a function yet. This is a method. but it can easily become a function. It can become a curried function, okay? So this provides us the flexibility of defining these things at different points, okay? But if you try to, so first of all, let's just do it together, right? Here we're going to add 2 and 1, and there we go. We're going to get 3. Happy, happy. Okay, great. But suppose you wanted to say, don't do this, especially don't do it at home. Val, you know, my curried add succinct add. Okay, so hey, you folks out there, don't do that at home. Okay, if I tried to do this, error, bad things will happen. Okay, it'll be unhappy. It'll be unhappy. It's saying it's missing argument list. And you say, well, what use is this curried function? This is a curry gone bad. This is a curry that's gone rancid or something. We don't want to use that. But ladies and gentlemen, in fact, we can do it. It's just we need a little bit of finesse. All we have to do here is we have to do this. Okay. We have to put a little thing here to indicate a missing argument list. And this actually turns it into a partially applied function whose job in life is to take an int and return an int. It does things. So now, okay, this shouldn't be called bad one. I could call it good one, but no. Let's just do this. Okay, so here we are. His job in life is to add 2 to things, right? So we'll give it a 7, and he will return back a 9, or she will return back a 9. Okay, so this is how we use this kind of method with multiple return lists. We basically say, hey, don't yet. I'm not going to give you the later ones. Give me back one that's partially evaluated, as we say. It's a partially evaluated function. It's evaluated only for this guy and not for the other. Okay. And in general, we can do this to turn a method into a function. We can use this underbar to kind of bring it into to being a function here. Okay. Now, it turns out in the book, they used multiple argument lists, but they used them for a different purpose. What was their purpose in using multiple argument lists? Does anyone remember? They used it for type parameterization. They wanted to achieve type parameterization. And it turns out that if you have a type that's recognized by the first argument, then it can use that information in knowing what to expect for the second argument, for the second argument list, I should say, parameter list. So if it could figure out what sort of types it's dealing with in the first parameter list, then we can use it in the second parameter list without having to explicitly specify it. Okay, I'm not going to go into that, but that's how they use it in the book, and there's an example there of them using it, which you know, you can go take a look at. Now, this is a general thing. So, for example, we could have def my method, and it takes an argument and it squares it here, and then I can say, whoa, sorry, I meant to capitalize that, and here we are. And then I could say, my, val my method function here equals my method. And what's the magic notation I have to give? What do I have to give here to turn it into a function? Underscore, yeah, we just do underscore. And here now it's a function. So again, methods in Scala have a couple advantages. They can have multiple parameter lists explicitly. They can be type parameterized. And I think there's one or two more, but this is a way that we can convert them into functions, and by converting them into functions, we can readily, apply them to, we can pass them around as functions, etc. Okay. So that was a little thing on methods, functions, currying. Currying is key, ladies and gentlemen. Currying is key. And I won't go into it here because we don't have time. There's quite a number of things I still want to cover here. But suffice it to say that currying may shake some of you up. And if it does, if you have an unsettling feeling about it, it's for good reason, quite possibly. Because to deal with currying, we can't rely on our classic activation record stack frames that we used in currying, where in classic, imperative programming or object-oriented programming, where each time we have a method called, we create a new frame on the stack. We have a set of parameters with that frame, and as soon as we return from it, those things are taken off the stack. Because somehow it needs to remember A, much long after that original call that provided A. It needs to remember this A long after the time where we called myAdd succinct is over. So when we do this, when we get this value back, my curried add succinct, this is long after the call to my curry add succinct with 2 returned, that we're able to use this thing here to evaluate, adding 2 to 7. So it's somehow remembering this A long after that call has returned. It's remembering up here this A long after we called curried add and got back the result. So in a classic handling with stack frames and activation records, you call a function, it puts on a bunch of things on the stack, like the arguments to the function, the parameters of the function. While we're in that function, we can use them. They're sitting on the stack. The activation record is sitting on the stack. We can use them, and then when it returns, they're all gone. Here, they can no longer be gone. They have to be remembered around, potentially. And it turns out there's whole technologies for allowing that in a viable way that we don't have time to go into, but I have other lectures where I talk a little bit about that. Okay, ladies and gentlemen, any questions about that before I go into another key topic that will be very helpful for the rest of the course? And it's a topic that was covered also in the chapter. Other questions? Okay, ladies and gentlemen, I am now going to introduce very useful construct in Scala that was introduced in the chapter for different reasons, but it's going to be very important in the Spark context. It can be very important in the context of our work. So it's something called, it's a type of class, but it's a special type of class called the case class. Okay. And the first thing I'm going to do is introduce a regular class. It's class non-case class. Okay. And the syntax, ladies and gentlemen, for classes in Scala is going to likely be new to you. And you saw it some in the book. But we're going to have, like, I'll say non-case person, okay? Non-case person, okay. They're going to have an age, and they're going to have a name, a string, okay? And I am going to, in fact, just define this as a class. And now, oh gosh, oh, I don't know that Zeppelin supports this. Oh man, I might have to switch to the Scala shell to demonstrate that. I actually haven't tested this in Zeppelin. In the Scala shell, you can do Java P, and I could say Java P non-case person. And I doubt it's going to work here. I think it's going to say, oh, I'm unhappy. So I'm going to switch over, and some of you may wish to do so with me. Hi. Others have which you may just want to look at this. I'm going to switch over to the Scala shell just so you can see this. Okay. Now the projector isn't working, so we're viewing things over the web. Do you have it recorded? Record.
Yes, I can.
Record now. Yeah. So here, I'm going to say Java P non-case person. And this is in the Scala shell. And it will actually show information about this class, okay? It's going to show all sorts of information about that class. Typically, I'm not interested in all that information. I'll say here I want to see private things in the class, but not all the extra stuff. And it'll actually show me what it turns into in Java. Scala works behind the scenes with Java, the Java virtual machine. And this is showing me kind of the equivalent components of this. And you'll notice what it's created. Where did this, what is this thing here? Everyone in this classroom knows Java. What is this here? What is this thing that I've highlighted? That's begins with a C, ends with an R. Constructor. It's a constructor of the class, right? And you'll notice that I defined it this way. This is defining the default constructor, the so-called primary constructor in Scala. And it turns out classes are primary constructors in Scala. But now I'm going to do something different. This was a regular class, a non-case person, okay? Now I'm going to create a person case class. And I'm going to do this in this one, then I'll switch back to Zeppelin and we'll continue on in Zeppelin. I just want to be able to use this Java P thing, which we can only use in the Scala shell. Okay, so now I'm going to say case class person. And they take an age and a name. I was going to do income, but I'll just, because time is running short, we'll just do this. I'm going to say case class person, okay? Now, we'll get into what case classes are, but basically they're used for almost invariably read-only classes. They're immutable, and they automatically support a wide variety of operations. And they can, by virtue of that, including their support for unapplied, they can be deconstructed and used in a particularly flexible way. But they're used to capture the sort of immutable needs. Now, I'm going to do the same Java P here for that, okay? I'm going to do this same thing. And what you'll see is that this is a class. It's a class like the other one we created. But this class has a bunch of things auto-defined for it, okay, that are routinely needed. An example is it knows how to copy itself. It knows how to test equality of itself in a common way. Yes, it created this constructor, but it also knows how to manipulate itself in some ways that are extremely useful. More than that, it knows, and I'm going to have to see how we do this. It has what's called a companion object. And the companion object knows how to take it apart and put it back together, okay? It knows how to build it without saying new person. We could just say person of this, okay? So earlier, we defined a thing called non-case person. That was a class, remember that I defined earlier? I could, by virtue of defining that, in Scala, I could create a non-case person. I could say, you know, val and CP1, that's my non-case person, new, and I have to pass it the things it needs, which I told it. So I'm going to pass it an age, and I'm going to pass it the name, you know, Joe, right? There it is. That's an instance of that class, right? Just like in a classic Java. Now, for the case class, I could still do that. I could still say, here's my person one, okay? Here's my person one. There it is, right? But more to the point, I can also do this. That's also a person. Okay. So case classes give me a particularly abbreviated way to do this. Now, the way this is supported is through what's called the companion object. There's actually the class, but then there's an object, which basically is kind of like a singleton. We use it in the same way we use so-called static methods in Java, which are things that operate on the class as a whole. Okay, so that companion object lets us construct it. But what is much neater than that, ladies and gentlemen, is it lets us destructure it. Lets us not only put it together from its pieces, but take it apart into its pieces. And that, it turns out, is how matching works. And that is how a lot of things in Scala that are beautiful work. Okay, so we've created these two persons. I called the second one Joe. I don't want to do that. I'll call this Sue, okay? And she's going to be 50 years old. Okay, so we have two people, Joe and Sue, okay? Here, and they're different ages. Great. Now, what I'm going to do to show you how you destructure this, and this is a very important point at a practical level, we're going to use it a lot. You do val, and I'm going to say, here we go. So we're going to take it apart into pieces, and the syntax here is a little bit confusing, okay? Let me show you one way I could do this. I could say val age. If I wanted to get Joe's age, I could do person1 dot turns out age. Okay. I could mumble. Get age. My memory about this is a little bit vague. We might not be able to do that easily with a case class. Give me a second here, because I'm pretty sure that with this came. Oh, of course. Sorry, folks, I forgot to do a key thing here. Right. We'll say val this. Okay. Now this is telling me these are read-only things. These are immutable. And as a result, it's actually a little bit. And of course. Why couldn't I get it? Age. Sorry, folks. I called it A before. Man, I should give myself a licking. That's horrible. That's horrible. Talk about non-intentional revealing name. That was the key thing. Now, I also do want to say val because it means they're read-only. But by virtue of this, I'm going to go back and define Joe. Okay. And I'm going to define Sue here. Okay. Now I could say p1.age. There we are. Okay. And I could say, hey, I'm going to have a variable, a value named known as age, and it's going to be Joe's age, right? Something like that. I can do that, right? But watch this. Ladies and gentlemen, watch this. This is cool. Okay. But more to the point, it's useful. Okay. I can say val person age comma name equals person1. I'm taking it apart. I put it together before out of pieces, right? I put Joe together. I specified age and I specified name. Here, I'm actually taking it apart. I'm taking a reference to Joe and I'm destructuring it into his age and name. If that reminds you of matching, it's for good reason, because matching does the same thing. When you match on an expression, it's actually taking into pieces. Remember the H colon T? Remember that? We did that earlier with the matching up here. That's how it's doing that. It's taking it apart into those pieces in the same way. And it turns out that this becomes extremely useful in many contexts. We can loop over them. We can take them apart, in other words, in a loop, and each time go through, do things. If we don't care about some features, like if we didn't care about their name, we could just take their age alone, etc. Okay, now I'm going to import, and forgive me because I've been falling out of sync here with this other one, and so I am going to copy all of these, and I'll go back to the comfortable confines of Zeppelin. Okay, so here we go, because I want my Zeppelin session to be limp-like and supporting the broad set of things. Wait, got that? Okay, good. Okay, this is basically what I'm doing in the Scala shell, and I define Joe, and here we go. I could access this, otherwise I could go on there. Okay, happy. Oh, okay, now how do I get on? Okay, it's going to be unhappy if I try to execute this, but I'm going to let it be unhappy, and as long as it gives me a new one. Okay, happy. Okay. Okay, ladies and gentlemen, next, we're going to import scala.util.random. Okay, here we go. And now I'm going to create a population of people. Okay, vector.fill. So if you haven't done it in your Scala shell, be sure to do these things. So create a case class like this with age. Ignore this first thing here, age. This should be age and name, and you can go on and have that. And now we're going to fill up a vector, which is a different sort of collection here, with 1,000 people. Okay, and what we'll do is we will create persons, okay? And the persons, we're going to be specifying their age and name. So we'll draw their age from a random number uniformly distributed between 0 and 100. And we will draw their name from a random string. And we can get that we're calling next string of 3, okay? Although these will build names that are more easily recognizable by some of us than others. Okay, so this closes that, this closes that, and this closes that. So what is this doing? What is this thing doing here? Does anyone remember? It's creating what? What is that creating?
Creating 1,000 victims.
1,000 of these, that's right. And are they all of the same person? No. No, it's passing this in a lazy way, which means it gets evaluated for each thing. Okay, there we go. I don't know what this person's name is, but maybe someone can pronounce it. You want to try? What's his name? I don't think. Maybe it's yeah. These are not familiar things. I think sometimes there's what's that? Yeah, it's Korean characters. Yeah, exactly. Okay. Okay. So, ladies and gentlemen, here we have 1,000 people. Now, having done that, what we can do is actually we could do, for example, go through here and right. We could write. So one thing we could do here is we could say population dot for each. I'm sort of triaging my comments here. For each, and for each person in the population, for example, we could report out their name, right? So for each person, by the way, for each takes a function. So for each person, we could do print ln my and I'm gonna just show this to you. I haven't had time to formally introduce it, but name colon. I don't know why. Why is it that it's oh, because I guess it's in the quotes. That's why. Name colon $ name and age colon $age. Oh, sorry. P. Yeah, we have to do this awkward syntax, and that will be the point I'll get to. Age, we'll do p dot age here in curly brackets. Okay, and oh gosh, this is horrible. The color is abysmal, actually. Okay, come on. We want this. There's a $sign around that, and then we escape. Okay. So we actually don't want this thing. We're going to get it to print out for each person their name, rank, and serial, their age. Oops, age is not a member of person. Oh, did I not? Oh, of course, I didn't define it in here. So let me just go do that. That was in this block. I didn't actually correctly evaluate. Here we go. So boom. Let me go and okay. How can I? The dream of centuries. Okay, that's great. Boom. There's person with age. You folks already have it, probably. It's just I didn't. I hadn't evaluated that here. Okay, get down here. Okay, there we go. And then we'll go like this, and it should print out. Okay. Oh my gosh. Okay, there's a lot of them. Okay, so ladies and gentlemen, this is substitution syntax. Basically, it allows you to indicate what things you want to substitute in, and it's particularly awkward here because the thing we're substituting in here is actually an expression, and so we have to put these curly brackets around it. But we can do much better than that with destructuring here, okay? So what we can do is we can actually say population dot, or sorry, we could say for, here we go, for person, age, comma, name, within population. And then we can say print println. Actually, I don't think we need this. Println substitute. This is a substitute string, so it'll allow us to substitute in, and we will say name colon $name, age colon $age. We could just use without curlies because they are variables, and we should be able to do that. Okay, so here it's actually binding each person here in the population, destructuring themselves into their age and name, and then using it appropriately. So this whole issue of destructuring, which we saw in match expressions, the fact that we could earlier on take things apart into its constituent pieces like this, it's supported for case classes automatically, and it allows you to have many conveniences in life, including the ability to kind of take them apart through a value declaration. Again, I'll show that here, or to take them apart in a for loop, or to take them apart in a match expression, etc. So we saw this earlier with value. It may have been before UN arrived. So I'll just show that here. Oops, P1. Oh, I need to say val P1. Sorry. There we go. Boom. And here we go. And then I can destructure it so I get age and name extracted from them. Okay. It turns out case classes in Spark are very important. we will be using them a great deal. And it's one of their nice features is that we can destructure like this. And that will afford us sort of an economy of expression that we use. And in general, we use these companion objects a great deal to build the objects, to destructure them, to be able to define a set of sort of routine operators on them that come along with case classes. So in general, for many contexts, we just use case classes rather than using classes. Case classes provide a set of additional functionality, which is really useful and actually helps us in common tasks, that much of which is provided in the companion class. If you want to read more about case classes, you could do so. Here, particularly. There's some things related to getters and setters. They provide apply methods to create, unapply, to take apart, and to allow for things to be for apply to be invoked on a tuple of values. They are immutable, and they automatically include sort of a val field for various parameters. And I show how these works in various contexts in those slides that are provided. The companion objects, for the most part, we don't have to worry about them, but they make it really easy for us to do things like to build up objects and take them apart. Okay, so returning now to a few other things I just want you to pay attention to. We've covered a number of these things, including recursion and currying and abstraction via parameterization. Data sharing was something that's a very important point that was emphasized in the book. The reflection being that if we have an object which we want to modify, and it's not immutable, it's mutable, we can change it. At a general level, what that means is it often has to be copied. It has to be copied so we don't stomp on someone else who's depending on the current values of it. We want to modify it, but maybe someone else has to still have access to the original, and as a result, we have to copy it. It's called defensive copying, and it's talked about in the book. And what that leads to is when you have mutable data structures, a lot of copying just in case it's required. And when things are immutable, it turns out there's less copying and you can build things out of them more readily. I'm going to have a lecture, which I think I'll ask you to take a look at. It's about, it focuses on Scala because of the class context, but, excuse me, on Java. But it talks about this issue with mutability and its implications for building structures out of mutable or immutable pieces. And what you'll find is that it's much easier to build things out of immutable pieces. And among the other reasons is it means you don't have to copy. Okay. We talked about companion object. We talked about multiple parameter lists. And I gave reference to its use for type inference. And talked about the special Scala syntax for lists that are very useful. The other issues here are less central, and I'm not going to go into them. Things like variadic functions, things that could take an arbitrary number of arguments. We'll be using them a lot. By and large, we won't have to define them. Okay, so for next time, I'm going to assign an exercise over the weekend for you to undertake that will expand on some of these components. But our focus next time will be chapter 4. And this chapter is going to get into the issue of error handling and get into really our first encounter with monads that aren't just collections. And I'd like you to go through that, and we're going to be exploring those in class using something that's not really talked about, interestingly, in the chapter much, but it's the try monad. So we'll be talking about the implications of this. The chapter will give motivations, etc. And we'll introduce one of the monads that I'll talk about, which is either. But, and I think option, it may, yes, it talks about option as well. And option is absolutely central to Scala programming. Option is very, very important at a practical level. And it's very useful for the Spark context too, okay? Because it's used in Spark APIs, for example, quite a lot. But we'll also introduce try, which is of great value when you're dealing with large amounts of data, as is option. Okay, so that's all for this time. I will try to go back and post my code to people, and maybe my JSON file I'll also share so that people can download it if they wish to do so. Okay, thanks very much, and I'll try to post that set of material by tomorrow, including the exercise if I can. Okay, thank you.
Thank you.